Everyone. Thanks for joining. Taking a break from the F word today, but we will be doing that tomorrow. I got something a little bit different for you this week. We're going to talk about deploying parallel WEKA file systems with an auto-scaling Slurm cluster on Google Cloud using the Cluster-Toolkit. So if you're not familiar with any of these things, that's okay, because I will be giving you an overview of all of this. And at the same time, I did want to demo what it is we're doing. And because it takes some time to actually create those resources, I am going to kick that off now. So I'll kind of walk you through from like a high level what the user experience is like when you deploy this. And I'm going to kick that off to the side and let things deploy. And then I'll get into some more background information and sort of like what it is we're actually doing here. So let me slide in my VS Code window here. So at a high level, what Cluster-Toolkit allows you to do is to create what's called a blueprint, which is really just a YAML dictionary that lists out the resources that you want to deploy. And high-performance computing, or AI ML, infrastructure on Google Cloud consists of tons of components, which can become very complicated if you wanted to write all that Terraform infrastructure as code independently on your own. And so what Cluster-Toolkit does is it provides sort of a higher level set of modules to deploy individual components. This could be things like file systems, like the WEKA file system that we'll be doing today, or file store, or Lustre file system. You can deploy compute solutions that have various schedulers. So Slurm, in this case, is what we're going to be talking about today, but you can also deploy a PBS job scheduler, for example. And at any rate, the idea is you can take these composable modules, define them in a single blueprint, and use the Cluster-Toolkit binary to then create the Terraform infrastructure as code, so that you can then manage more complex infrastructure in a way that follows best practices from each of the contributors of these modules. And what we've done is add in a custom module that currently sits in its own repository for the WEKA file system, so that you can combine that with other modules that exist in the Cluster-Toolkit. So at the command line, all I'm going to do to start, I'm just going to go back through my commands here, because I did work this out a few times, so hopefully everything goes smoothly here. But essentially what you need to have in order to get started, of course, is a Google Cloud project, the gcloud CLI, Terraform CLI, Packer CLI, and then of course you'll want to download and install the HPC toolkit. Well, what used to be called HPC toolkit, it's now called Cluster-Toolkit, from Google's GitHub repository. I'll have links for that in some slides, also in the description below. There's links to all that stuff. So yeah, we're going to call HPC toolkit. We're going to create our Terraform infrastructure as code from the blueprint. Once that's done, this creates a new directory for us that contains all of our Terraform infrastructure as code. Here I've called it AI ML Slurm WEKA. So that's the intended use case that we have for this particular example in mind is for those of you who are doing AI ML training and inference on GCP. Once we have that, we can go ahead and just run the single command deploy. I'm going to kick this off to the side. Once I hit deploy, there's a few prompts that will come up just to make sure I'm accepting each of the things that are going to be created sort of as we go. So if it looks like I'm distracted from time to time, all I'm doing is, oh yeah, let me overwrite, because I did a demo on this. Oops. Yeah, let's do that. Like I said, every live demo, there's always, oh, I know what happened. We're going to go back. We're going to create one more time, and then we don't want to deploy on the YAML. We want to deploy on the file. Let me fix that real fast. Okay, and then we'll just deploy AI ML Slurm WEKA. If I would just follow the instructions, this would be easy. Not create, we want deploy. Off to a rocky start. There we go. Now that's going. I'm going to kick that off to the other side here. And let's go through some background information for those of you who are interested in kind of what's going on here. So a lot of this did come from some of the work we did for Midjourney over the past couple of years. Of course, we couldn't have done it without our friends at WEKA. Been great working with both Midjourney and WEKA. If you're not familiar with Midjourney, they are I would say a synthetic media AI art company. They have a really cool Discord server where you can go in and use text-based prompts to generate images and graphics, things like that. So, for example, you might say /imagine an oceanographer. Me, hi, I used to be an oceanographer. I guess I still am, but I do a lot of other stuff now. An oceanographer giving talk to, let's say, some Googlers about high performance computing. Wouldn't that be so weird? And Midjourney's tool will generate some pretty cool images that are quite convincing. This might be an oceanographer. Look, they all have beards. Kind of looks like me. Not really. I mean, they're just white guys, so whatever. Or you can imagine something even crazier. Maybe different things that may or may not be real. Let's imagine a photo of a UFO floating over New York in the 1970s. And so here's a few sample images of this, what the tool can create. It's pretty cool stuff. I'm not going to pretend to understand a lot of the details about how they go from point A to point B on this. Those guys over there are quite talented, and they make some very cool, fun toys to, I would say, products to play with. When I look at this problem, so I wear a few hats in my life. Of course, yes, I am an oceanographer. I do applied math. For the last 6-7 years, I've really gotten into Linux system administration and particularly cloud computing side of things. And I've started to put on a perspective of, rather than being an HPC user, of being someone who might design infrastructure or administrate infrastructure for other people to use for their work. Let me get some speaker notes here so I keep myself on track. The deal is, what I've often found, and this is not specific to Midjourney, this is often the case with anyone doing experimental research and things like that. Researchers often don't necessarily know, and I wouldn't say everyone, but the majority certainly don't seem to know exactly the kind of compute resources that would be most beneficial for their application. Most of the time, at least the traditional HPC, folks are sort of given compute resources and asked to adjust their code to that platform. When public cloud came around and Google Cloud, for example, as we'll be talking about today, it kind of flipped that problem on its head, where now you have this choice of the variety of compute platforms you have, not just like CPU type or GPU type, but you also have topology questions like how many cores per node do I have? Do I want to enable or disable hyperthreading? Should I use compact placement or should I not? You have tons of options for your NICs. I mean, this opened up a whole world of questions of not just how could I adjust my application to fit the hardware I'm running on, but maybe how could I choose the hardware to be most beneficial for my application. And this is not certainly an easy question to answer, but it opens up quite an attractive field of exploration when you're designing these systems. So when you look at something else like people who are doing AI ML, typically you're looking at either two branches of this. You're doing training, or you're doing inference, and each of those has their own requirements in terms of like memory per job and how much memory needs to be on a GPU, whether or not the application can do multi-GPU, etc., etc. It gets quite complicated. And so what we tended to approach this problem with on Google Cloud is to set up an auto-scaling Slurm cluster that basically gave access to as much variety as we can find in a single Google Cloud region, and then expose that to users using Slurms. They have a thing called features where someone can put in basically a list of constraints in their batch header for Slurm, or in their salloc command to select out the kind of hardware they want, so they can experiment. So at the end of the day, it's what you really have to do to answer this question is you need to get an easy way for your users to be able to experiment with all the options that are out there so they can find what works best for them. Let's talk about workflow requirements, particularly again focusing on at least Midjourney's use case. But again, we see some of these things I pulled from other projects we've worked on in the past. We have one set of folks that we often encounter, and there are interactive users. And these are people who are typically working on developing new applications and creating new workflows before they go into production, but they want to do it on the same system, so with the same job scheduler, and be able to play around with the various resources that they have. Typically, when things are being developed, they're usually only on a single VM to start to really get things going, and it's often best, we find, to just use on-demand instances for this, particularly because the auto-scaling instances on GCP, there is some lag time. It's not a lot these days. I mean, we're talking 3 to 5 minutes to get a compute node, but those little bits of productivity lost that can cause context switching is quite important to avoid. So that's one camp of users, our interactive users. When you think of them, think small jobs. We really want those instances available whenever they want them. And then once the applications are developed and they're starting to run at scale, at least in the AI ML space or in the bioinformatics space, we've seen what we would classify as high throughput computing, where you have hundreds to thousands of jobs running the same thing, but possibly on different input. I would say, embarrassingly parallel in the sense that each of those individual jobs do not depend on each other. This is much different than like computational fluid dynamics or other use cases where people are using things like MPI, and those thousands of processes need to be tightly coupled to each other. So in the kinds of use cases we're looking at today, and I'll be mostly talking about these high throughput folks, again, they're looking order of hundreds to thousands of virtual machines. We're okay with preemption because, if I get, 20-30% preemption and those jobs have to rerun, we'll pay that price to have a little bit extension of our wall time for a cheaper cost. So that's one set of features we need to incorporate into our cluster. Well, now this part's quite interesting, and I can actually refer you guys to another resource on this probably after the fact. I forgot I left this bullet point in here. But we find that a lot of, particularly bioinformatics and AI folks, like to work. They're mostly Python developers, and they tend to like working in IDEs like VS Code. And we did find that there's some need to have Python debugger support on the compute nodes. Again, I'll make sure I update the description in the link after this to drop in a. We have an example repository on how to integrate your Python debugger with Slurm. So yeah, typical job workflow for a lot of these Python developers, it's basically three steps here. We load a software environment. Sometimes this can be like 8 to 12 gigs, and even bigger in some cases. If you're using PyTorch already, that's an 8 gig footprint, and it's tons and tons and tons of Python files. Those need to be loaded from disk somehow, and if that's over a network, then that's going to be a heck of a lot of metadata IO. Over your network file system or whatever you're using. Then there's the application run, which on training and inference. So on training, it's typically either the data is already stored somewhere on a shared file system, or that data is being actively scraped to a high-speed local SSD or NVMe disk, and the application's reading from that and just trashing it as it goes. I guess I'm focusing particularly on file systems because that's what we're talking about today. And then on the inference side, typically it's just loading model weights and those kinds of things from disk. Again, that could be shared file system or some kind of block storage where you're just doing a gsutil, CP, whatever, to get it onto your local system. And then there's generally a small amount of cleanup. So that's kind of what the footprint looks like for AI ML, at least from our perspective. As someone who just kind of monitors the system and keeps an eye on what's going on. When we think about how you want to create a software environment for these kinds of people on Google Cloud, there's two categories of software that we think of. Things that are evergreen, so things it's not generally changing very often, and there's not people are generally not too picky about like the versions that you're going to be making available. And then on the other end of that spectrum is, specifically for those who are developing new applications, a lot of times the libraries and tools are a moving target, and there is a bit of pickiness about having certain versions available, at any given time. And as an administrator, it can be quite cumbersome to have to deal with those kinds of things on a day-to-day basis. Ultimately, yes, it'd be great if once you nail down versions of things that you push them into the evergreen category, so you make it more stable environment for people, much easier to use, makes you more effective as an administrator to be able to answer questions if you really know what's going on. But on the other hand, you do want to provide your users some freedom to pick their own libraries and tools. So on the evergreen side, our solution for this is using VM images. So basically, SCEDMD provides a set of VM images that come pre-baked with the Slurm job scheduler and a number of built-in tools to integrate with Google Cloud. So we usually use that as our starting point, and then we bake everything in on top. In a lot of cases, like rootless Docker has been a popular request. So we have a rootless Docker integration with Slurm that has come together quite nicely, minus some issues with the network performance if you're doing things like web scraping. I'm happy to talk more about that down the road. And then usually, like I said, there's some in-house tools that kind of stick around, and this is something I would say is pretty common in terms of what you might want to have in your stack if you're doing AI/ML on GCP with this particular solution. For those moving target solutions, we've seen two strategies here. One is to just have users manage their own Python environments out of their home directories. And if the home directories are served across the network, then you just need a network file system that's going to be able to keep pace with loading all those Python environments whenever you spin up like 1,000 nodes and you need to do Python env activate or what have you, or a conda activate. Because we did provide rootless Docker, some users do make use of Docker images. So that would be from the artifact registry on GCP, which does tend to scale a little bit better when you're doing very, very large runs for high throughput computing. But they have there's pros and cons to each of that. With Docker, you have to maintain some kind of registry and a build system and all that stuff, which can put some structure in your life as a user, and it's not a bad thing. But it removes your ability to be as nimble as someone who can just create and delete Python environments in their home directory. So and all these solutions are fine, they're good, and they have their time and their place. That's I guess really what I'm getting at. But these are the two ends of the spectrum that we typically will think about. Sorry, I'm accepting the next thing here. But the reason I bring up the VM images is I will need to bring this up when we talk about how we handle the WEKA file system portion of it. So one of the things that ends up being evergreen in the solution that we'll be talking about today is of course the WEKA file system agent that needs to be available so you can mount WEKA across your cluster. So let's go ahead and move on to the next slide here. I guess, yeah. So what we found that it seems to be a sweet spot for training and inference, at least as a really good, I would say, mid to high tier point. I mean, you could probably get away with a much smaller system than what I'm quoting you here, but every HPC center has their own way of doing things. I don't think we usually try to model ourselves after what you would find at a typical HPC center. So you usually have some home directory space. Often that actually tends to be much lower than what I have here as our data or our simulation workspace. But we opted to flip that on its head. As a lot of users tend to work out of their home directory, so we keep home at about 10 terabytes across. I think that's a fair amount to work with for about 20 to 30 users. That home directory, there's no purge policies on that part of the system. People are allowed to keep things there as long as they like, so long as we're not running out of disk space. On the data side, we did have we look at typically look at like a secondary mount point of about 1 terabyte where you can do faster file IO, those kinds of things. A lot of times folks do want to have like multiple snapshots so that in case there is some kind of event that happens and you need to recover your system or any of the files you might have, you should be able to do that. And so when we were looking at file system solutions for Midjourney particularly, we kind of kept all these kinds of things in mind. We did play around with a few solutions like Lustre so DDN Lustre. We looked at the file store, and it was just not those things were not really appropriate for the kinds of activities that were really becoming bottlenecks with basically what I would call Pythonic high throughput computing, which again is applicable to things like bioinformatics and stuff. The WEKA file system, honestly, in our opinion, it kept pace, particularly with the metadata operations after a bit of tuning. So all the stuff that we have here, I'll summarize what the architecture is that we landed on. This is what we're end up deploying basically through that simple blueprint that we've provided. We have 3 components. You have Slurm-GCP, which consists of this login node that people use to actually access the cluster, a controller where the Slurm controller daemon and Slurm database daemon run, and then you have all the compute nodes where the actual work is done. Each of those instances, the login controller and compute nodes, mount their network file systems from a WEKA file system in a dedicated, what's called a dedicated backend configuration. And to handle the snapshots, WEKA provides a nice deployment called SnapTool that you can use to schedule regular snapshots to be done, and those can also be duplicated back to Google Cloud Storage, so completely independent of your cluster, which is quite handy. The last bit here, I'm not going to talk about today, but there is a Grafana dashboard that we put together using a nice open source project called Prometheus Slurm Exporter. Definitely go give those guys a star on GitHub. They absolutely deserve it. And we combine that with Wekamon, so you have full monitoring of that cluster. But that's not part of the blueprint yet. That's still down the road, should there be a need for that from the community. Let's talk a little bit about some of the best practices. I need to introduce some concepts about WEKA and Slurm. First, so this is a conceptual diagram of a WEKA file system deployed in this dedicated backend infrastructure. On the top part here, you have what WEKA will refer to as clients. These are things that are going to mount the file system from the backends. The WEKA backend servers on the bottom half are dedicated to hosting with it's 4 separate processes called the front end, drive, compute, and management nodes. All of these are responsible for all the file IO operations to a set of local SSDs. So this is just one way to deploy WEKA. The other way WEKA can be deployed is in what's called a converged architecture. And in the converged architecture, basically the front end client will also run with the drive, compute, and management nodes. And what this allows you to do is if you have a static cluster where your compute nodes are always there, you can set up each compute node to be an equal participant in the WEKA file system. So the file system is not like the compute nodes and controller. You can deploy them all in that converged node. So I bring this up because you should know there are other architectures out there for WEKA, but the one that we use on Google Cloud and the one that we're providing in the blueprint or in the Cluster-Toolkit module is this dedicated backend infrastructure. So on the other hand, we look at Slurm. Slurm, we think about 3 different kinds of nodes. As I mentioned before, we have what's called a login node. That's typically where users will SSH into the cluster and interact with the job scheduler. We have compute nodes where when jobs are submitted, that's where the work is actually being done. And then you have the controller, which is set up to do all the workload management and job metrics and database stuff. We have 3 daemons. You have Slurm-D, which runs on both the login and the compute nodes. And you have Slurm database daemon and the Slurm controller daemon. If you're running in what's called a configless mode, what you can do is, and this is how Slurm-GCP works, is you can set up a single Slurm configuration file on the controller and tell Slurm-D to look to the controller for its configuration. That way you don't have to manage a whole bunch of configuration files spread across the cluster. When we combine Slurm with WEKA and a dedicated backend configuration, essentially what we're doing is putting the WEKA front-end process on the login and compute nodes. If you're mounting to the controller, you would also have it running there as well. So this is the one of the checkboxes for that evergreen software that we need is we do need that WEKA agent installed so that we have the WEKA front-end client running on those instances there. And then down below we have the dedicated backend server. So the Cluster-Toolkit up until this point has provided the login controller compute. It provides Slurm-GCP out of the box. What it did not have was a module to deploy WEKA file system. However, WEKA does have a Terraform module. It wasn't quite compatible out of the box with the way Cluster-Toolkit works. So basically, all the work that we did was to basically kind of glue WEKA's Terraform module into Cluster-Toolkit, and then set up some examples to show you how to set up the appropriate networking infrastructure, bake a VM image on top of SCED-MD's Slurm-GCP image to add the WEKA file system agent to it, and then deploy Slurm and WEKA together so that you could actually have all of this stuff done correctly. I mentioned done correctly. I think I have some slides here, on some requirements. So WEKA does require a minimum of 4 VPC networks. So each WEKA backend actually has 4 NICs attached to it. Now the supported instance types that WEKA has given their stamp of approval for Google Cloud are the C2 Standard 8 or C2 Standard 16 with local SSDs. So you need to have those local SSDs there. I didn't talk about this too much, and I won't go into too much depth here, but there are 2 types of mounts you can do. One is using a DPDK mode, which is definitely good if you have applications that have high bandwidth needs. If you're going to use DPDK, your Slurm compute nodes and your Slurm login node needs to have at least 2 NICs. The first NIC needs to be reserved for Slurm communications, and the second one needs to be dedicated for Slurm to WEKA, and that's a minimum. I mean, you probably should have more, but that's one requirement there. You also need VirtIO networking type for the DPDK. And then GVNIC is recommended for UDP mode. So UDP mode, you don't need multiple NICs. So the little thing I didn't mention here, basically, if we're running, in addition to Slurm daemon, we have the front end client now running on compute nodes. That front end client is going to consume some memory, and if you're in DPDK mode, it will consume cores on your system. So you need to use what Slurm calls specialized resources to set those resources aside for that WEKA agent. Now, the nice thing about our blueprint is we've taken care of all of that for you. Those things, at least for our UDP deployment, which is the only one we support at the moment, has the specialized resources set up for you. Okay, like I said, I'm not going to go into too many details about all the best practices, but I highly encourage that if you're going to use this system, you check out the docs.weka.io, so the WEKA documentation. We worked with them late last year, earlier this year, to get this documentation put together that has some guidelines on how you should integrate WEKA with Slurm, what we have found to work quite well. So if you scan that QR code, that should bring you there. If not, down in the description, I do have a link to that page. Now, Cluster-Toolkit. So we've talked about Slurm-GCP. We talked about WEKA. I've been rambling here and there about Cluster-Toolkit. I guess I'll set just a clear stage here. You can get Cluster-Toolkit. It's Go code that you can find up on GitHub. So it's github.com, Google Cloud Platform, Cluster-Toolkit. It's an open source software offered by Google Cloud, which makes it easy for customers to deploy AI, ML, and HPC environments on Google Cloud. Again, the way it works, as a refresher here, is you write a simple YAML file called a blueprint. That blueprint uses modules. Now, these modules, there's a whole bunch of them that ship with the Cluster-Toolkit, but you can also use external modules from another GitHub repository. That's how we exploit, or we make this whole thing available, is we put up our own Cluster-Toolkit compatible module just to start kicking the tires on this, and hopefully at some point we'll get this merged into a community contribution. But at any rate, so you have your YAML, and once you have your YAML, you'll pass it through the Cluster-Toolkit binary, which combines your YAML with the modules that you have listed in there to then create all the Terraform infrastructure as code. Once the infrastructure as code is created, you can then either manually go through and Terraform create each one of them. You can certainly do that, or you can use the GHPC binary to manage the deployment for you, and create your cluster and all that stuff. So that's kind of nice. Again, our module, so down in this bottom portion here, the cluster modules, among the other things that we use from Cluster-Toolkit, we've added on our site, so our GitHub, so github.com/Fluid Numerics, there is a module called WEKA+/GCP Cluster-Toolkit. That is what is being used to create the WEKA file system, to provide the stuff to bake the VM image, etc. If you go there, there's an example subdirectory, which I'll be walking through here shortly, that will show you kind of how to get started here. What's up? Oh, thank you. Oh, getting the buzzy buzz on the cable. Okay, I see. All right. So I think that is all I had prepared on the slide side. So let me go ahead and bring the code back, which I think we're still on track here. And I'm going to just walk through some of the code that we have. And I guess I'll pull up on the repository rather than... So I guess I'll pull this over so you see where things are at. So we're still creating, which we're almost there. We're almost there. It's creating the WEKA file system. Once that's done, we should be able to see the Slurm-GCP cluster being created. If I go into Compute Engine for this project, let me hit refresh and see what we've got going on here. So yeah, we've got our actual instances here for the cluster. Basically the WEKA Terraform stuff, they have a startup script in there that goes through and installs the agent on the back end instances, and it will actually start to provision the cluster. And what I'm looking for is there's this column in use by. Basically it groups all these instances into a managed instance group. Once that's done, the cluster is clusterized, and everything is kicked off from there. Let me go back to the code here. So this is the GitHub site for that WEKA+/GCP Cluster-Toolkit module. There's licensing stuff. You can read over that on your own time, but there's the overview, which is the thing I probably said in 10 different ways today of what this is. In the README, you will find all the things you need to have before you get started to make sure you're not going to run into problems. So again, Google Cloud CLI. Of course, you need a Google Cloud project with active billing. And oh, I'll pop this over. Look, WEKA is clusterized. Hooray! And now we're creating the Slurm cluster. Yeah, you will need Terraform and Packer. These are command line tools from HashiCorp to help you. Packer is used to create virtual machine images, and Terraform, of course, is to actually create and manage your infrastructure. You'll also need to get a download token for the WEKA agent software from WEKA. So you'll need to go to get.weka.io and just create an account and get a download token. And then, Google Cloud with active project. Now, in the examples directory, so yeah, at the top level, it's basically all the glue that's needed to make the module happen. I won't go into that today. Maybe in a future live stream, I'll go into some of the guts here, but it's not terribly long. I'm sure if you've done Terraform before, you can figure out what's happening. Let's look at the example. So we have one right now. This is the AI/ML/Slurm-GCP 6 WEKA 4. At the very top of that example, those are the two variables that you really need to set. That's your project ID, where you want to deploy those resources, and then that WEKA IO token that you've downloaded. Other things you may want to set, it's up to you. Just make sure you choose a region and a zone that have C2 standard instances. You will need those for WEKA, and I believe the default Slurm cluster we've provided also deploys L4 GPUs, and so the G2 standards are the G2 instance types, and we have A100, so you'll need to just pick a region that has both of those. But if you use US East 4, you'll be fine. The rest of this you don't really need to set, but I'll walk you through kind of what's being created. So the first block here is creating a network that's used just for the image baking process. So image baking, what that is what Packer does for you under the hood. Is it's going to create a compute engine instance using the starting image that you want to start with. So for us, that's the SCEDMD Slurm-GCP Ubuntu 24 image. And then it runs a startup script on that, and then it will take care of tearing down that resource, snapshotting the disk into a VM image, and then cleaning everything else up from there. So we create a network for image baking. We create a startup script, and this startup script is what's used to install the WEKA agent, and then it also configures one of the settings that we need for WEKA to play nice with Slurm. Particularly, we want Slurm assigns resources on a compute node using C groups, particularly CPU sets, is where you might run into some conflict with WEKA. If you don't turn off the isolate CPU sets in WEKA, WEKA will attempt to change the C group settings after a job's been allocated, which can cause some confusion about how many resources are actually available for a Slurm job. So definitely turn that off. That's again, this is all taken care of for you inside of here. The next group is the Packer group. It's going to create the instance for you. So again, the source image that we're using, sorry, I misspoke. It's the 2004 Ubuntu from SCEDMD. So this has Slurm in it already, and then it's just going to add the WEKA agent to it. If you did need to install other software, you can just add to that that script, or you can just add another install script and then add it to your use list. The next group of resources is our cluster. So we do need to set up a multi-VPC network. So this is how we get our 4 NICs for WEKA. So that WEKA NICs number is going to be set up in your variables up top. Let's see here. Where did I put it? Yep, WEKA NICs number 4. Yeah, so we use the multi-VPC, and then because Slurm-GCP only needs one of those networks and not all of them, we create the primary VPC from the first multi-VPC network that's created. So that's all that block does there for you. Then we have the WEKA-FS cluster. We do have a fork of that at the moment that's pinned to a specific version. We're working on testing that against WEKA's WEKA GCP HPC toolkit, but that's basically it there. We're going to deploy the WEKA file system. Oh, sorry, no, that's our module. That's my apologies. That's our Cluster-Toolkit module. Now the local mount, this is the directory where you want to mount the WEKA file system to. Now this blueprint out of the box will only do one file system. We are working on, I think it's in our issues actually, to work on adding support for more mount points, but that's what we got for now. We have one mount point. And then everything else below is stuff that you can find documentation on in the Cluster-Toolkit repository. You're basically creating what are called CPU node sets, so groups of nodes that can be used as compute nodes in the Slurm cluster. They've got a CPU node, it's C2 standard 4 on demand. We've got our A100s, we've got more A100s, but these are 8 GPU A100s. We got our L4s, so the G2 instances, more G2s, but multiple G2s per node, so 4 of them. Yeah, just a variety of compute nodes. We create a partition, create a Slurm login node, and a controller. Now on our deployment side, everything's done. So I'll open up the Compute Engine console. And aside from the rocky start, this was actually pretty darn good. So up top, again, we've got our dedicated backend WEKA file servers. And then we've got our Slurm controller and login node. And here's the moment of truth. If I SSH into this thing and it doesn't brick on me, I'm going to be so happy. No, I'm serious. I've tested this quite a few times. I think we'll be all right. So once I get in here, of course, you can do the usual things for Slurm, make sure things are live. Hey, here's all my compute nodes. Great. Let's do df-h to see what I've got. I've got my home directory mounted from 10.0.0.4, which is the first WEKA instance up here. We are working on resolving some bug. It's like ideally with WEKA, you want to like provide a few of the backends in a comma separated list so that if one of the WEKA backends doesn't respond because it's super busy, you want to be able to fall back to the other backend servers. But at the moment, from the blueprint, we can't do this. There's some compatibility issue with the Slurm-GCP startup process that again, I've got it documented. I believe in the issues there, but hey man, you got to start somewhere. At any rate, yes, that's our WEKA file system deployed with Slurm-GCP. I don't have much else to talk about, but I hope you found this interesting. Let me take a look at the chat here, see if anything's going on. And if not, that's cool too. Da, da, da. Well, if the chat, I'll hang here for a few minutes in case you guys do have questions for me. I am going to go ahead and tear this down. I guess I'll show you how easy it is to tear this down. It's quite nice. Let me get the VS Code stuff open here. Once you've got it created, let's see. We want destroy. Yes, you basically just run HPC toolkit or Cluster-Toolkit, I think is what you'll find on the newer version. Destroy AI, and you just give it the directory where your Terraform stuff is, and it will go backwards through the infrastructure. So, and here I have that same example we were looking at before. What it's going to do is basically walk its way back through each of these, kind of tearing things down in order. Yeah, most of the work we did was actually in, I'm going to go ahead and apply, in making this cleanup process quite nice. So WEKA does this very interesting thing where they actually will, in their Terraform, they don't actually deploy those compute engine instances. They deploy cloud functions and Google Cloud workflows that then in turn create the instances. So Terraform has no idea that those instances exist. And actually, I think that might be a good segue to show you the main TF here, just because to hint you in on some of the work that was done to make this possible. So yeah, here's our WEKA deployment. Now this module from WEKA, which is the Terraform GCP WEKA, like I said, it's going to deploy cloud functions and Google Cloud workflows. It has no idea that those WEKA compute engines exist. So we have to create this null resource to, one, wait for the WEKA cluster to be ready. So you saw earlier when I deployed it, there was that section where it was saying, oh, wait for WEKA to deploy, and then it said WEKA is clusterized. That's this bit here. It basically waits for a maximum of 25 minutes running this little script, which is really just a do loop with a sleep in it if the cluster isn't clusterized, to check if the cluster is ready. Now, when you go to tear down, this is a really hacky way to do this, but it works. I gotta say, it just works. So we use this Terraform data resource. We call it destroy WEKA backends, and what we do is we run a local provisioner only when the Terraform resources are being destroyed. Again, timeout of 20 minutes, and we run this terminate cluster. And because this is so stupid, because Terraform data, you, you can you have to send in things through environment variables. So the input that we had to send in was a come on, get out of here. It was a concatenate. So it's a pipe delimited list that has the URI from the WEKA module for the cloud function that you use to destroy the WEKA backends. And then that function also needs the cluster name. So we needed to pass in those two things. The local exec provisioner underneath Terraform data can only take in one environment variable. So we had the pipe concatenate those and set them as an environment variable. If I pull open that script, let me see if I can do that. That terminate WEKA script, all it's doing is a curl statement to that cloud function with the name of the cluster, of the WEKA cluster, in the arguments there. That bit was probably the most frustrating thing to put in, but it now works and everything cleanly can be taken down when you go to destroy your cluster. And previous attempts at doing this is we would have to go through and manually destroy the cluster with the cloud function ourselves. This way, Terraform just does it for you. So yeah, let's look back at the compute engine UI. Hey, my connection failed because guess what? I destroyed that cluster, and it's all going away. So now that it's all cleaning up, again, if you guys have questions, go ahead and post them in the chat. If you want to chat and you can't, that's probably because you're not a subscriber. You need to subscribe to the channel in order to participate in the chat. So if you want to chat with me, subscribe, post your question in the chat. And if I don't hear from you guys, I'm going to go ahead and skedaddle. If you are into Fortran stuff, tomorrow at 3 p.m., I'll be back again. And we'll be talking about some really cool stuff with object-oriented Fortran and GPU programming. All right. Well, thanks for tuning in. Let's go ahead and turn this shit off. Thank you, sir.